Okay, so second two problems here on the first page. Like I said in the last video, they're related to each other, and this is another kind of attempt to highlight how common ion effect is important. So the first problem here is just a weak acid. We're going to calculate what's the percent ionization for this solution of the weak acid. And the second problem is where a common ion is going to come in. We're going to use, we're going to try to calculate the same thing, percent ionization of the weak acid, but now it's a solution that contains a common ion. The sodium benzoate, or butanoate. Butanoate would be the conjugate base of butanoic acid. So now butanoate is going to be coming from the dissolution of the sodium salt, but also from the equilibrium we're looking at for the weak acid. So for the first part, just the weak acid, we know a weak acid, we can just abbreviate as HA. We don't really need to know what the formula for butanoate is. It's going to protonate the water to a certain extent, depending on the value of K, and that will result in conjugate base being produced. Now we're given the initial concentration here of 0.075 molar for the weak acid. There are no products yet. Change here, we're going to lose some of our starting compound, gain some of the products. So by equilibrium, this will be 0.075 minus x, and x. Now, as usual with this type of problem, we want to consider, can we get rid of that minus x, make this problem a little easier to deal with. So in this case, we want to take the concentration of the acid, divide it by the Ka, right? And we said our guideline there is if that's 1,000 or higher, then it's pretty reasonable to make that assumption. So if we take 0.75, divide by 1.5 times 10 to the minus fifth, oops, that is 50,000. Now that is pretty good. Nope, it's not. I left out a zero. So I think it's probably 5,000. Yes, it's 5. I left out the 0 and the 0.75. 5,000. So the assumption is okay. So let's get rid of that x when we go to solve the problem. And that means Ka here. Now, we know Ka is products over reactants. I think we should be at a point where you can see where we're plugging in already, products, reactants. So Ka here would be equal to x squared over 0.075, and we were given the Ka of 1.5 times 10 to the minus fifth, right? So we just have to solve this for x. So 1.5 times 10 to the minus fifth, multiply through by 0.075, right? And then take the square root of that answer, and I get x is 1.06 times 10 to the minus third, and that would be molarity here. That's going to be the concentration of hydronium, concentration of A minus. So in this case, where we're looking for percent ionization, right, like any percent, that's going to be part over whole. The part is how much ionized, right, which would be this concentration for the conjugate base, so 1.06 times 10 to the minus third. We're comparing that part to the whole, which would be all of the weak acid we started with, or 0.075, and then we multiply this by 100, reference it to 100 to make it a percent. So that previous answer divided by 0.075, and then times 100 gives me 1.4%. So I've got 1.4% ionization in that particular solution. Now, the comparative problem here with the common ion effect is how is the dissolution or ionization of this weak acid going to be affected by having some of its conjugate base already in solution? So same equilibrium that we're looking at. Right? But a little bit of a change to the initial conditions, and what we'll be able to kind of evaluate is how does that affect the percent ionization in the sample. So initially, still 0.075 molar for the weak acid, but because we have a sodium salt. Now we know sodium salts are always soluble. Sodium's +1, butanoate's -1 here. The conjugate base of a neutral weak acid is going to be -1. The initial concentration here is going to be 0.085 molar in the conjugate base, right? Instead of 0 like it was in the previous example, right? Now that means we're going to get plus x here, right? So minus x here, minus x here. Now this shift forward is going to be reduced by the presence of a minus, so that means this x is even less relevant than it was in the previous example, right? And that also means this minus x compared to 0.085 is also not going to be relevant in terms of a change to that concentration. So we're going to ignore both of those x's. Sorry, that's a plus x, not a minus x, in this calculation. Right? And really it'd be kind of hard to handle a problem where we couldn't make those assumptions, because we'd end up with lots of x terms, and we'd have to go through some serious math to solve that equation for x. Okay, plugging this into Ka, right? Again, it's products, so that's going to be 0.085 times x over reactants, 0.075, right? And Ka was 1.5 times 10 to the minus fifth, right? And we want to solve this for x. So 1.5 times 10 to the minus fifth, multiply by 0.075, and divide by 0.085. That'll isolate x on one side of the equation, and that gives us an x value of 1.32 times 10 to the minus fifth molar. Now we can see that's quite a bit less than it was up above, which is what we would expect from sort of a Le Chatelier's principle analysis. If you think of adding in the conjugate base as a disturbance to the equilibrium, it's going to push it back this way, which means less of the HA is going to dissolve. Now in terms of percent ionization, we again would take the part, which is how much ionized, divide by the whole, which is how much of that weak acid we started with, and scale it to 100 to make it a percentage. So if I take that previous answer and divide it by 0.075 and then multiply that by 100, that would give me the percentage, and that is 0.018%. So big difference, right? Quite a bit less soluble when we throw in that common ion of the product of the reaction. All right.